Alright, welcome back everybody. In this video we're going to talk about exponential growth and decay. And we lead off with saying, there are many situations where the rate of change of a quantity is proportional to that quantity. And in all of those quantities, we're basically looking at an equation of this form right here, dy dt equals k times y. And what this is saying is the change in the variable y with respect to time is some constant times that variable y. And the initial value of y is y at time 0. If we take this differential equation and integrate it using separation, we show you here, we arrive at this explicit formula where whenever we have a quantity that changes at a rate proportional to the amount of the quantity, y is equal to y sub 0 e to the kt. And that is what's known as the law of exponential change. And we can use this model in a wide variety of different circumstances, and we're going to go ahead and do that in the examples that follow. So let's start with example 1. Suppose you deposit $5,000 into an interest-bearing account that compounds interest continuously. So it compounds interest continuously. When it does that, that means that the amount of interest is proportional to the amount of money in the account at any point in time. And so we're going to use a model of the form y equals y sub 0 e to the kt, where the y sub 0 is the amount that's deposited initially, and the k value is the rate at which it changes, which is this interest rate, which we're going to convert into a decimal. So the first question, our model is y is equal to 5,000 times e to the 0.038 t. So how much will be in the account after 5 years? 5 is our time. And so we're just going to go ahead and put 5 in for t. And we can calculate how much will be in the account after 5 years. So I'm going to go ahead and break out my calculator. And I've got 5,000 e to the 0.038 times 5, and I end up with $6,046.24. I'm going to round down to the nearest cent, since it hasn't quite reached that 25 cents, $6,046.24. All right. How long will it take for there to be $10,000 in the account if the interest rate is 0.2 or 2.5%? So now our model is slightly different. The interest rate has changed. It's 0.025 t. And we want to know how long it's going to take for there to be $10,000 in the account. So we'll put $10,000 in for the amount. And we need to solve this for t. So I divide both sides by 5,000. Take the natural log of both sides. And divide both sides by 0.025. And so I've got the natural log of 2 divided by 0.025. And according to this, it will be approximately 27.726 years at this interest rate before there's $10,000 in this account. All right, the last one here. What interest rate will lead to $8,000 being in the account after 4 years? So we're going to take this y equals 5,000 e to the kt, and we're solving for the interest rate this time. So we're going to put $8,000 in for the amount in the account. The amount in the account. And solve this equation for K. I divide both sides by 5,000. Take the natural log of both sides. And divide both sides by 4. And calculate that out. Natural log of 1.6 divided by 4 gives me 0.1175. So the interest rate would be 11.75%. All right, continuing on to a different application. A radioactive element decays in such a way that 80% of the sample remains after 5 days. What's the half-life of this element? Now, we're starting off here with the law of exponential change, y equals y sub 0 e to the kt. And in order to answer this question, we're going to measure time in days, but we need to figure out what the rate constant is, what this value of k is. Well, we're told that 80% of the sample remains after 5 days. To write 80% of the sample, that's 0.80 times the initial amount that was there. That's how much is left. And so now I can solve this equation for k. In order to get the rate constant, I divide both sides by y sub 0. Take the natural log of both sides. And so my rate constant is the natural log of 0.8 divided by 5. And when I'm solving for something like this, I like to leave the rate constant in exact form instead of putting it in as a rounded decimal. Since it's in the exponent, small variations in the exponent can lead to larger variations in our answer. So I like to leave this as exact. And so now we have the model that y is equal to y sub 0 e to the natural log of 0.8 over 5 times t. And we want to find, in part A, the half-life. The half-life is when half of the amount of the original is available, or is remaining. And so we're looking to solve for time when half of what was originally there is remaining. To solve this for t, we're going to divide both sides by y sub 0. Take the natural log of both sides. And then isolate our t by multiplying by the reciprocal of what's there. So t is going to be 5 times the natural log of 1/2 divided by the natural log of 0.8. And now I'm in position to calculate this. So I've got 5 natural log 0.5 divided by natural log of 0.8. And I get that the time is 15.531. And so the half-life of this element is approximately 15.531 days. All right. How long will it take for 90% of the sample to have decayed? If 90% has decayed, that means 10% is left. And so we can set this up with the equation 10% of y sub 0 is equal to y sub 0 e, and the rate constant remains the same from what we found initially. And now we can solve this equation, and that will tell us how long it takes for 90% of the sample to decay. I divide both sides by y sub 0. Take the natural logarithm of both sides. And multiply by the reciprocal. And the amount of time that it will take for 90% of the sample to decay will be the value I get when I calculate this out. So I've got 5 natural log of 0.1 divided by natural log of 0.8. And it will take 51.594 days. Oops, I forgot what that number was already. 51.594. Okay, that was a few examples of how we can use the law of exponential change, and also a little bit of narrative in the beginning about why this relates to separation of variables. We can really develop these models from the separation equation by integrating if we get stuck and forget what the law of exponential change is. But that's probably a little bit more than we'd like to do. It's probably best if we understand that this formula works for any kind of scenario where we have a quantity that changes at a rate proportional to how much of the quantity is there. Alright, that's the end of this video and the end of this lesson, and in fact, the end of this unit. Hope you guys have a great rest of your day, and I'll see you next time.